So, so if we consider the analog instruments, so what type of instruments actually are considered as electronic analog instruments? So first of all, it's voltmeters or ammeters. So generally, there is of course a type of ampermeter as a device. So both voltmeters, ampermeters. So they may be the DC, AC, a special type of so-called pulse voltmeters that are thought to measure the amplitude of the pulses, and there is a multi-mode voltmeter that may be switched on between different kind of modes. For the voltmeters, for the electronic volt, we actually discussed a little bit design of electronic meters, and there is some special type of measurement amplifiers used in the voltmeters. Generally, the generators are considered as analog instruments too, despite they may be actually digital and provide a waveform in a digital form. They still is used to test an analog circuitry, analog processes, and they are maybe considered as analog devices, despite they are actually digital by their design. Another type of, so, and here we actually made a split in two different forms, so in two different groups. One group is harmonic waveform generators. It may be a very high accuracy, provide the harmonic waveforms. And then another example, it's a function generator. They may provide a less accurate waveforms, but in a various shapes, starting from the same. Usually they may provide the same harmonic waveforms, but they could provide a rectangular waveform, triangle waveforms, and so on. Generally, there is two ways when we use a generator. So when we use them for the test circuitry, we usually doesn't require high accuracy, but I use them for some kind of calibration measurement. In this case, we actually have to provide a very high accuracy, especially in the reproducing of the frequency. Another group of the analog instruments we consider are RLC meters, which are thought to measure the resistance, inductance, inductivity, and the capacitance of the corresponding elements. They often are bridge type circuits, and we discuss these bridge circuits in the next class. The oscilloscope certainly is a type kind of analog instrument, despite they are actually modern oscilloscopes. Most of the modern oscilloscopes are digital instruments now, but they are thought to depict an analog waveforms. Another type, it's a phase meters and frequency meters, which should be considered as analog instruments too. In spite of the way that in fact they are. So we actually could consider nowadays analog instruments as instruments that are thought to operate with analog signals. Not with a digital signal, but with analog signal. Speaking about different kind of electronic voltmeters, so generally the design of the direct transformation or direct chain electronic voltmeter just include the minimal design for the DC voltmeter includes the amplifier, the DC amplifier, which often has a function of scaling. The output meter, this may be electromechanical device, mechano-electrical device, and usually the design of such kind of measurement instruments include one high gain amplifier and one measurement device, and the arrangement or of the measurement scale is done just by using a voltage divider. Even in a professional meters, the voltage divider is a very nice decision how to adjust the range. We don't need anything except a voltage divider. The voltage divider has some breakdowns. Sometimes the voltage divider may be joined with a buffer in front. So if we are going to have a voltmeter with very high input resistance, we may add additional follower which operates in a very high range, but still the divider in the very first stage is it's fine. For the AC, we may have a little bit more complicated structure. So we still have a divider to adjust the range, but we need afterward we usually use an amplifier, IC amplifier, and we use some kind of active rectifier to prevent the voltage losses and signal losses because of the forward bias of the diodes. So here we need actually to amplify and use a rectification. So the direct rectification, as it was previously, we have seen this circuit with a direct rectification. Such kind of circuit is not an optimal because actually it's 0.8 volts when you measure voltage using the silicium diodes, or 0.3 volts for the germanium diodes, but it actually provides some distortion in the measurement. For the precise, for the accurate voltmeters, we actually have to use some kind of circuitry which compensates the non-ideality of the diodes. The output of the electronic voltmeters not necessarily just will be a signal, mechanical devices. Already nowadays it's maybe analog digital converters. This provide actually the signals already in a digital form. So we will discuss the design of a digital voltmeter when we discuss design of the digital devices. But generally we have, if we're going to come from an analog device into the digital one, we actually add a final stage with a scaling amplifier and analog digital converter. So the scaling amplifier function is just to scale the output signal that is directed to the mechanical device into the input range for the analog digital converter. For the transducer, speaking about this part, the transducer from AC to DC. So there is another type. We just a little bit extend our discussion about the AC-DC transducers by just analyzing it a little bit small, analyzing on some different type of the transducers. So if I if you take a look at on such kind of circuit, we just use one diode, but we add. So if you look at our previous for the AC-DC conversion, so we see that we have here actually an amplifier or voltmeter. It was driven directly by these semi-waves produced by diode. If we add capacitor to our load, we have to note that for the electronic voltmeter, one of the advantage of the electronic voltmeters that they have really some buffer in the input. For the precise, for the accurate voltmeter, we even may have a instrumental amplifier as a first stage, and then all these stages. So when we are, especially when we're speaking about low voltages, when we rather have to amplify than reduce the voltage, so we may have an input and an instrumental amplifier, the input stage. Well, anyway, so if we're going to convert this, yes, if we use such kind of circuit, we're actually adding a capacitor and some load resistors, and we just measure with an instrumental amplifier on some other amplifier the output voltage. So how the output voltage looks like, just because of the capacity and the positive semi-wave. When we have some positive pulse, and now it's not important whether we have a harmonic input signal or we have some kind of complex shaped signal. So we may have a pulses. So when we have a pulse here, so the positive pulse actually charge the capacitor, and when the pulse drops down and the voltage here drops to 0, the diode becomes reverse biased, and the capacitor to discharge only through the resistor. Of course, it depends on how resistor's R is big. Whether it's very big, the capacitor discharge very slow. And if we adjust the value of the capacitor and the resistor, so we may get a situation when the next pulse comes. So the capacitor will not be discharged yet, and the next positive pulse recharge the capacitor up to the top value. And in this case, we have actually nearly constant DC voltage with some pulsation. Of course, the amplitude of pulsation and much of how frequently the pulses come and what is a time constant of this RC chain, of this RC assembly. Well, so for the very fast coming pulses, we may actually get here nearly DC signals, which it will be difficult to see this pulsation. And anyway, what is another important thing, that if you look at what will be the amplitude of or what will be the level of the signal, average level, if we neglect this small pulsation, we will see that it actually is equal to the amplitude of the pulses, except of the bias voltage, which drops over the diode. So we have here the amplitude equal to the amplitude. We have this output signal. It will be an amplitude of the pulses minus direct forward bias of the diode. If we replace the diode with an operational amplifier, which includes diodes, so call it ideal diode circuitry. So this ideal diode circuitry may be explained like this, or noted like this. I try to draw here a little bit. So we already discussed it. So I may the diode, I replace it with such kind of circuit. We have a positive input here. Here I have the diode at the output of the operational amplifier, and I have here the feedback. So this circuit operates as an ideal diode. So it has no forward bias. It's actually not, I wouldn't say that it has no forward bias, but if I apply here some positive voltage, I will get here the same positive voltage. So the operational amplifiers compensate forward bias. If I have here some negative voltage, I will get here 0. So it actually works very well. So if I replace the diode with an ideal diode, I get an ideal peak detector. What else important? So I could, if that my pulses comes as a very short and frequent pulses, but the amplitude of these pulses change quite slowly, and these times of change of the amplitude, typical period of amplitude change, is much higher than time frequency, than the time constant of my detector RC. In this case, the output signal will have enough time, it's held enough time to follow the amplitude change. Wait a moment. Okay. Oh, so well, so and well, so and then our detector will actually proceed all these short pulses, or it takes the amplitude of all these short pulses, but as the amplitude change much more slowly, so the capacitor will have a time to discharge, and the output actually follows the amplitude. Such kind of detector have many names. One of the name it's a peak detector. Another name it's envelope detector. Why it's named as envelope? Because if we have a very high frequency pulse, the output will be, but high frequency pulse of, let's say, not so small duration. So the output will be actually the envelope of the amplitude of these pulses. So we got the enveloping. Another way, so this type detector, peak of envelope detector, is very often used in modulation of the amplitude modulated signal. So we have an amplitude modulated signal like this. So we have some oscillation. So we have some oscillation, which amplitude changes following some other regulation. If we send such a modulated signal into the peak detector, we will get output which oscillates only as an amplitude. So we actually got a low frequency signal, we got the demodulated signal out of the highly modulated. So the peak detector is very useful circuit. Of course, the more is difference between the periods or typical characteristic times of the amplitude change and characteristic time of the pulses itself. So the more accurately the detector works. So we have to have a big difference into the periods of pulses. So the period of pulses should be much more less period of the amplitude change. In this way, it works very well as an enveloper. Here is another example, the average value detector, just relatively depicted. And one more, so please make sure that the if we consider this detector like an IC-DC converter, so then the out is equal to amplitude. Generally, it's already maybe enough. So if we know the shape of our signal, so if we know that it's a sinusoidal signal, we get that we know that U effective for the sinusoidal signal, it's U amplitude divided by square root from 2. For other type of signal, we may recalibrate actually this output as for any type of signal. So this is another example. This is an average value detector. So when we actually have a output signal, output current that pass through the load in any way, it doesn't depend what the input signal is, positive, negative. So we always have the current, always have a current flowing through the load detector in a one direction. Here we have a plus, here we have a minus. So actually the voltage drop over the resistor RS will be full rectified. Adding a low pass filter, just adding a low pass filter, we will get the average of this signal. So in fact, the output of the total output of this average value detector is proportional to the integral because of the filtering parameter. It's a average of the absolute value of the input. So it provides an average value. We remember that the average value will be different in respect to the effective value for different different shapes too. Yeah. So here's another example. The feed here is used to stabilize more or less the current, to get the current through the bridge and through the to get actually current through the bridge constant and proportional to the voltage. So if the current through the bridge will be constant, so that the amplitude of the current will be constant, so then the amplitude, which actually the voltage amplitude of the voltage over RS will be constant too. Here's a quite complicated circuit. Here is a more primitive circuit when actually RF-CF works as a filter. And for the average value, so if we look at what will be the output of such kind of average value detector, how it will be related with the amplitude, so we will find that the relationship between the output and amplitude will be different. So here is one relationship, here's another for the rectangular one, and here's another for the triangular one. And A here is just a gain of the corresponding amplifier, some coefficient which is depend on the gain of the circuit. Yeah. So we see that the relationship between the average value and the amplitude value is a little bit different for the different type of the signals. Here is an example of the equivalent converter, which this type of the converter, which use two thermocouple devices, transducers, so two type of couple device with a heater and and a thermocouple inside. So they are actually switched together in the output circuit in such a way that they are switched on in opposite directions. So the idea of this converter is the following. So the voltage, which is the alternating voltage, which is applied here, causes more or less a calibrated current that is going through more or less stable current that is flowing, alternating current that is flowing through the load, this heater. Actually, this is let's say a voltage to, it's an example of voltage to current converter using an op-amp. So the feedback here is used so to provide, so we apply voltage here, we apply here such certain voltage, and then op-amp increase the output current till the voltage drop over the resistor R will be equal to the input voltage. So here is actually, it actually converts input voltage into the current, which equal to input voltage divided by R. So it's not, we don't use just a resistor, because the resistor may be thermally, especially if the resistor, it depends much, its resistance on temperature. It may change with the temperature, it may change with some other, it may be heated by the input voltage and change its resistance. This voltage to current converter, because of the feedback due to operational amplifier, keep the current always constant. So we always have the current more or less constant. So the current actually we have and another feature of this circuit is that it has a very high input impedance. So we convert voltage into current not via input impedance, but via infinite impedance on the amplifier. So here is probably the most important reason why we do use such a circuit. To convert voltage into current, not just by adding this voltage over the resistor. So, and we actually keep this current proportional to U in divided by R. So current is stable more or less. So this current causes the electromotive force to appear here. And this electromotive force, as it appears here, it's provided voltage between, as it the electromotive force on this thermocouple will be higher than the electromotive on this thermocouple. So the total voltage here will be positive, and we cause the, no matter, actually we have some voltage here. Voltage causes the current to appear through the output of this amplifier. And this current will grow until it will be so high that the heating of the second thermocouple will become equal to the heating of the first thermocouple. Then they got this electromotive force compensated because they switched one opposite to another, and the voltage here will drop. So in any case, so we have here actually the balance. So we rise up the current to counterbalance this rise in the electromotive force because of heating of this of this heater. And finally, and if you consider it, and with all the mathematics, we actually find that the current which appears here, the AC current, it will be a DC current. It will be equal, in fact, to the current which appears. Otherwise, we will not get the system into balance. So it has to be the same. So if current E1, alternating current, provides some certain heating effect, so then the current I2 should to provide the same heater effect, then that means that this current has the value equal to the effective current value of this AC current. So actually got what we want. So we pass this current through the same resistor R, and output voltage will be equal to the effective of the input voltage. Some comments on the amplifiers. So if we speak about amplifiers, we certainly have to mention the direct couplet amplifier, which is nothing to discuss actually. We discussed it to a great extent when we discussed electronic circuits. So the direct couplet amplifier is just a chain. So it's just a chain. When we have one amplifier, then we have the second amplifier, then we have the third amplifier. So we have a direct chain of the amplifier when we got an input voltage, and here we got an output voltage. Nowadays, using the operation amplifier circuits in all these direct amplifier, we get quite robust design, which is not so sensitive to temperature, which is not so sensitive to some pulses in a power supply and so on. But not always this direct couplet amplifier is good enough, especially if we have a very high level of noise that could be added somewhere here and there. So we get a noise which is added at any stage of this amplifier. To work with a signal which has a high level of noise and may have a high level of noise, the MDM technique or a locking, it's much more useful. I switched now to the Latvian presentation. I'm sorry, I have not translated it yet, but I put the corresponding translated design already in Ortus. So you will have, when you review this lecture, you will find already Latvian, an English version. So speaking about the MDM amplifier. So MDM stands for modulation, demodulation. So you see that in Latvian it's very similar to English. So modulation, demodulation. So what does it mean? So if we have some original signal, the original signal of certain form, we provide the modulation of the signal, for instance, by alternating the amplitude of the so-called carrier signal. So we have discussed a little bit of modulation. So we have a carrier signal. The signal is it's a change with a certain frequency, and the frequency of 0 should be high enough comparing with the frequency spectra we're going to pass using the original signal. So then we change the amplitude of this carrier with the shape of original signal. So we will get finally the spectrum of the modulated signal looks like this. So it will be shifted to the F0, and if the original signal occupies some band in vicinity of the frequency of DC signal, something here, so the modulated signal actually occupies the same band, but in vicinity of the frequency of F0. If F0 is high enough, the relative width of the spectrum of signal will be much more lower. So of course, it's actually clear. So if, for instance, for the ACG signal, the spectrum is about 150 Hertz. So, but 150 Hertz from 0 to 150, the relative width of this signal is quite high if we take it comparing even with the middle frequency of these bands. About it's about 100% plus minus from some, let's say, 70 Hertz. If we modulate the signal with a frequency of, let's say, 10 kilohertz, then the band of the signal will be still the same 150 Hertz, but in respect to the 10 kilohertz, it will be very small amount. So then we use amplifiers, an AC amplifier. It is important that this have an AC amplifier that have an amplitude frequency response quite narrow. It works well, or it amplifies well only the frequencies around F0, plus minus small band. So we always have an amplifier with some narrow band. The width of band, the relative width of the band, may be as narrow as the width of the modulated signal, but we see that the modulated signal they may have quite a narrow band, and that means that when we amplify such a modulated signal with a narrow band amplifier, we actually cut out all the noises that may be out of our signal. So all the noises which has a higher frequencies, lower frequencies, and these have 0 plus minus small band, they all will be cut out. So when we actually after the amplification, the spectrum of the signal will be much more. The signal amplitude may be much more higher, but the noises will be. And then we put it into demodulation. demodulator, for instance, the same peak detector, get actually the waves, our waves, uh, of the amplitude. So we get out the filtered signal, so we filter it, we demodulate it, and we filter it. So we use a peak detector or enveloper, what we just discussed, and we got the output signal, which is already have a higher amplitude because the original modulated amplified signal have a higher amplitude, and we actually has a reduced noise. So this is one of the principles. The good example of MDM application, it's a spectrometric measurement. So for the spectrometric measurement, was a typical circuit or typical scheme, typical technique for the spectrometric measurements. So we have a source, here a light source, and we have a specimen which light absorption we are going to measure. So we pass light from the source through the specimen to the detector. But the problem is the detector, of course, the detector provides a signal which is proportional to the amount of light coming through the specimen. But if it didn't isolate all the measurement chamber completely from the stray light, we get the phone, some kind of ground light, so-called stray light. So it comes even, especially if you're going to provide some chemical reaction in the cuvette, in the specimen cuvette, and have to put some kind of tubing inside. And for this, we actually we have to open a little bit this chamber. It shouldn't be dark, completely dark. So we have some stray light, and this stray light may provide even a higher background than the signal itself. So we have a big background and very small signal. Work with such a small signal, and one of the way to cut out this background is to use a modulation here, and we use a modulation either electrically via electro-optic modulator or mechanically, but just using an obturator, some kind of a disc with holes cut inside. We make the light beam falling on the specimen to oscillate, to switch it on off, so it will be oscillating. If it will be oscillating, so then the detector accepts a signal from the background, which will be steady, more or less. Of course, it will change gradually due to the change of the daylight, due to the change of the sunshine, and so on, switching on off the room lights. And but on the base of this high and slowly changing background, we will get short pulses related to the signal just going from the source. So by the source modulating the source light beam, we get the modulated signal. Signal will be like that. So the amplitude of the signal obviously will be related to the amount of light coming through the specimen. So it's what we're actually going to measure, this amplitude. But we send it into the AC amplifier. The AC amplifier cut low frequency background, slowly changing background, and amplify only these peaks. Okay, it's even may, if it's really very narrow band AC amplifier, it may even cut a little bit the shape. So the output signal will not be this accurate rectangular pulses. They may be more or less the smooth pulses, but nevertheless the amplitude of these pulses will be related with the amplitude of light coming to the detector. So after the demodulation, we get the steady signal, which is actually proportional to the intensity of light coming through the detector. And then we cut, with this technique, we actually avoid the necessity to amplify the big background. We actually make the measurement so robust that it's even may be done. No, it's actually wouldn't say it could be done with the open compartment, but generally the compartment shouldn't be light isolated very tightly. So we may easily put there into compartment under the cover, put the tubing. So it's very robust to the stray light. So this is a good example. Another example, what we discuss, and probably for today, Another example, what we discussed for today, it will be so-called lock-in amplifier. Yeah. It will be so-called lock-in detector, or it's named lock-in amplifier. I consider this slide probably in English and then come back to Latvian presentation. So this is one of the most sensitive detectors that could be imagined. It works by the modulation demodulation too. It's actually user modulation. It's important that the signal that comes to the input of the lock-in detector or lock-in amplifier could be modulated with a certain frequency. Usually it's done by operating the measurement circuitry or the measurement equipment by operating it under a certain frequency. For instance, we may use this sine generator. So we usually have some kind of sine generator inside the lock-in amplifier, in the lock-in amplifier circuitry, and this sine generator is used to modulate the obtained signal. So one of the example, like in a previous example, we may use this sine generator to drive the electro-optic modulator. So the light through, it's harmonically modulated. Maybe another example, so it may be some kind of resonant mechanical system, and we excite this mechanical system with an outer excitation of the same frequency what the sine generator provides. So we have to excite our measured system with this sine generator, or through using this sine generator signal. Of course, we need probably some actuator between the sine generator and the experimental equipment. But the goal of this is to get the response to be modulated in the same sinusoidal way. So actually, now I probably switch back to Latvian. Yeah, because the text is the same in Latvian, is in English term. So this sine generator is used to excite the measurement system to get the response. So the response is actually will be the sinusoid. So it should be the response of the system will be oscillating at the same frequency as the sine generator provide, but it has, of course, another amplitude, and it will be shifted by, maybe has a phase shift. So this is a excitation is in phase with the generator, but a response may be shifted. Another example of the application of lock-in amplifier is the atomic force microscopy. When we have a small needle or teeny needle oscillating, and the signal, which is an optical beam, is reflected from this needle, and the oscillation of this optical beam over the detector provides the signal which has the same frequency as the oscillation of this teeny needle. And the needle is oscillated from the sine generator, and the same sine generator is used for the processing. So actually the needle oscillates with a certain frequency, the reflected beam oscillates with this frequency, and the signal what we take from the diode of the photodiode measuring this laser oscillation will oscillate with the same frequency. The input signal is oscillating with the same frequency. It may be quite teeny, so the amplitude may be very low, and it's usually is compromised with an amount of noise. So actually, the signal what is come to the input of the lock-in amplifier, it's usually the useful signal at frequency omega, it's a certain frequency, and a huge amount of noise of all frequencies. So what happens next? So we, of course, usually the lock-in include just usual amplifier, just AC amplifier, which amplify all together. The goal of this first amplifier just gets the signal to a certain level. So because the signal may be just very low. So we amplify it with a broadband or broadband AC amplifier. So, and both the useful signal will be amplified and not useful signal, noises will be amplified too. Then the signal is mixed with a referent signal from the sound generator. Here is a stage what is required between sound generator and a mixer or multiplier. It's a phase shifting circuit. So the phase shifting circuit add a phase shift to the sign generator. And actually this phase shifter is adjustable. So we may adjust it either manually or automatically to change the phase phi2. So we could change the phase shift of this generator signal. Then they are multiplied. After multiplied, they comes the actually low pass filter that operates as an integrating circuit. And this low pass filter cut all the high frequency oscillation, and the most important what the results will be. Finally, the results what actually come through the gain comes through the already DC amplifier, in fact, yeah, and to the output, it will be a signal which is proportional. Okay, it will be proportional to the amplitude of the reference signal that comes from sign generator and phase shifter, this U0, but it's a constant. We keep it constant and we know it. And another what the output signal will be proportional to, it's an amplitude of this input signal, US, and the phase shift between this signal and reference signal. This phase shift is a difference in phases between the input signal and reference signal. This comes from generator and phase shifter. Actually, when we regulate a phase shifter, we adjust the phase phi2 to be equal to phi1. And when they are equal, we get a maximal output signal. So, in fact, if this process comes quite long time, for a long time, yeah, for enough time. So we get here some constant voltage. And then we adjust the phase shifter. We regulate the phase shifter to change the phase phi2 until we get the maximum output. And when we got a maximum output, it means that the phase phi2 is equal to the phase phi1, and the amplitude of this output is proportional to the input signal amplitude, to U in. Now, of course, we have to know U0, and if U0 is exactly 2 volts, so the output signal in volts will be just equal to U in, to the input signal. So input signal, we understand that this is input signal that comes already here. We have to take into account that here was some amplification. Well, what is the corresponding mathematics of the lock-in amplifier? So let's consider the input signal before this after this first leveling amplification, but before the mixing, before the multiplication. So if we look at this signal, we get that this signal consists of the useful signal, which oscillates with a certain hour frequency and is phase shifted and has some unknown amplitude that we are going to measure, and noise signal. We may represent this noise signal as a sum, Fourier sum, of some noise components, which every component has their own frequency. So so the omega 1 here, the frequency with the index 1, is actually, we understand that it should be more correct to name it omega with the index I. But I just want to emphasize that here be the sum or all frequencies. Of course, the omega 0 frequency will be among them. But we consider the case when the omega, the particular component frequency doesn't match with omega 0. So the reference signal is just U0 sine t plus phi1. After the multiplication, so the two signals are multiplied. So we actually discussed how the multiplier looks like. So when we multiply the signal, we get two components. One is a multiplication of the useful signal by the reference signal with the same frequency, and we have here the sums where nearly all components except one with frequency omega 0 will have the shape of sinus omega 1 plus some unknown phase probably times omega 0. So this happens after the multiplication. Then to look what to transform these multiplications, we use identity, well-known identity, that the multiplication of the two signs is equal to difference in such a cosine. So if I multiply sine alpha by sine beta, so then I may transform it into cosine of the difference between alpha and beta and cosine of the sum of alpha and beta. So if I look what actually how my useful signal, which actually is now equal to the multiplication of the unknown amplitude of useful signal, known amplitude of reference signal, and oscillation with frequency omega 0 shifted by phase phi1 and shifted by phase phi0. If I do this, so actually I just understand that I have just take to divide it by 1. I have just take I actually use this identity. I take this one, then it will be equal to 1 of the u1 u0 by cosine of the difference plus 1 second u1 u0 cosine of the sum. So what actually I get if I do this? So the first member where I have the cosine of difference, the omega 0 t will shorten, and I get just the cosine phi1 minus phi2. And the second, I have to add omega 0 t phi1, omega 0 t phi2. I add them, and I get the 2 omega 0 plus phi2. In fact, what actually I got? I got the constant dc component. This is not oscillate anymore. Yeah, it's depend on the difference between phases, but it doesn't oscillate. There's no more omega t or no omega t component here. But this one oscillate as a doubled frequency. It's very high frequency oscillation. If I pass such a signal through the low pass filter, the DC component comes through, but the high frequency component will just cut out. It works as a filter. So if of course I have to select this RC constant of my RC chain, RC filter high enough to be able to cut out this double frequency and let only the DC inside. Actually, I'm interested only in DC, so my time constant may be quite high, because I'm interested only in DC component. Well, what happens with the noise signal? So if I look now at this noisy signal, for any frequency which is not equal to 0, 1, to 0 or to omega 0, for any frequency which is not equal to omega 0, I will get in the same way. So I actually replace the multiplication of sine by the difference in cosine. So, and I have get the first member in this sum will be cosine of omega 1 t plus 5 plus unknown phase minus omega 0 t and minus phase phi2 of the reference signal, and it will be sum omega 1 t plus omega 0 t plus these two phases. So actually I get here, after I make all my calculation, I get here oscillation with a frequency omega 1 minus omega 0, and here is oscillation with a frequency omega 1 plus omega 0. So this is a quite high frequency oscillation. So they will be immediately cut out by filter. By this one, it's generally it's oscillation of on a more or less slow, and it's very important, yeah, how far omega 1 is from omega 0. So when they are quite far, this difference will be high. But only for the slow, for the very narrow band around omega 0, this frequency will be low enough to give some kind of contribution to the final signal. But generally, if I look at this signal, so those one, the fast one, which has a frequency higher than omega 0, will be just filtered out by my filter. But this one, which has a lower frequency together, so it's some kind of low oscillation, nearly DC oscillation. If I look how the filter works with it, generally it's integrate. It's the low pass filter. First, it could be considered from a very point of view. One point of view, just cut out the high frequency. From another point of view, just and take and more or less the output of the RC filter is more or less the average of the signal. So if I look at the average, what is the average of the cosine over the period? So as the average of the cosine of the period, it's always just zero as an average from any harmonic function of over the period. And yeah, and moreover, yeah, RC. So it's actually the average. And moreover, if RC, if my time constant is high enough, this average will be quite close to zero. Even if I'm not so lucky and I'm integrated not over the full period, but it's integrated over half of the part of the period. Anyway, the cosine is a limited function. So it means that it is limited. It shouldn't be couldn't be bigger than some certain value. And then we divide the value by the time constant. The time constant may be quite high. So actually, this member, so this component, the contribution of this component will be more or less noticeable only when the frequency omega 1 is very close to omega 0. So it means that actually when we have a signal which is our component, useful component with the frequency omega 0, huge amount of noise of all other frequencies, the lock-in amplifier allowed to cut out these noises and amplify only the signal on the, and work or amplify only the signal with this frequency omega 0. So the selectivity on signal to noise ratio of lock-in amplifiers is really, really high. But it has some breakdowns. Yes, it has some drawbacks, and one of the drawbacks that we actually have to adjust this phase. Sometimes it may be done in modern measurement meters. It's often is done automatically when always some feedback system always whether we have a higher possible output, especially if we have a digital. Usually the lock-in amplifiers are controller driven. So when the controller actually all time just change this phase, just actually scan over this phase and record the resulting output, and then afterward with post-processing which I select in a certain scanning cycle what will be the highest output and which phase correspond to this. So we need actually operate the lock-in in some kind of digital device. We couldn't. It's not so convenient to operate it like an analog socket. It's usually operated as a digital device. Then we may provide such a measurement with a regular changing of the phase, and then looking at what when we go with the phase from smallest to biggest difference, and which difference we got a maximum. So let's say requires such kind of driving. Yeah. So some components of the lock-in. So the four quadrant, the full range multiplier, for example, as an example, the microchip AD835 could be taken. Yes, so it takes these differential inputs and actually multiplies this, providing the output in respect to 0, both in plus and minus. So it's actually such kind of microchip could be used to build a lock-in. Another element is a phase rotation. It's a phase rotation socket or phase shifter. So here is an example of the phase shifter inverting circuit. So it's provided it's invert negates a signal. So if you're going to get a non-inverting version, so we have to add an inverter afterward. So if we apply, for instance, a sine of 1 megahertz for this particular circuitry, so we may regulate with the position of the resistor R3. We may regulate the phase of the output. So it may turn it up to -19, from 0 up to -19. It depends on the position of the of the this resistor, so of the potentiometer. If high enough, so we get a maximal phase shift. If it's low enough, so we get a zero shift. Yeah. So then, yeah. Opposite. Yes, or when actually this effective resistor R3 is zero, the phase shift is zero. When it grows up, so then the resistor actually when the phase shift may go up to 90 minus 90 degrees. So we actually provide it's enough to have a phase shift within a 90 degree. Usually it's enough because usually the is not higher than 90 degree. If it's higher than 90 degree, but it's usually, yes, it's usually around the 90 degree. And finally, what we will consider today is so-called a photogalvanometric amplifier. It's a good example. I will look what I have in here. Yeah, it's a photogalvanometric amplifier, which actually consist of just already known. I wouldn't say that galvanometric amplifier is still in use, but they may sometimes, but they still could be in use because they provide a very high sensitivity and quite, how to say, quite robust to noises sometimes, and maybe even superior than any type of electronic amplifier, especially for the very low signal, and they are very well works with pulses in the form of so-called ballistic amplifiers. So the photogalvanometric amplifier is that we have magnetoelectric device with a permanent magnet with fixed core and a teeny moving coil, and this coil is springed too. It has two springs that keep it in a constant place, but it has no index. It has a mirror attached here instead of index. In the very first photogalvanometric amplifiers, the light beam was directed to the mirror and reflected translating scale when the light spot actually indicating the readout. So if the current flow through the moving coil, it deflects a little bit, and because it has no index, it's very lightweighted at very low inertials, and it may turn on a very small angle if the current is very small. But because of the just geometric amplification, so the low angle here may cause quite a noticeable movement of the light on the scale, and the highest is distance between mirror and scale, the biggest will be movement of the spot. And actually this is a basic of the photogalvanometric. So if we take the distance very high, we may even notice, of course, for the next generation, for the first generation, it was what just a focused light. For the next generation, it was already a laser, which was depicted, was what depicted on the mirror. And if we move the scale far enough from the mirror, we even may note the oscillation of flying spot because of the heat motion of the mirror. The brown motion of the mirror because of the fluctuation of the air pressure around the mirror. For this device really to work as an amplifier, not just a voltmeter. So the photogalvanometer this device is actually a photogalvanometer, which could measure a teeny pulses of voltage or teeny pulses of current, and even it may even measure single pulse, because when the pulse comes, will start to oscillate, and we could see the amplitude of this oscillation noted, and by this measure the total charge in the pulse, or total charge, I mean the product, the voltage and duration of the pulse. In fact, it's the total charge in the pulse. But how to make it an amplifier? And for the amplification, the light beam is directed into two, in all time was two photocells and vacuum devices for the measurement of the light intensity. Nowadays, it will be directed into two photodiodes, like this, for example. It's a element where here are already two photodiodes embedded here. And when we direct the light and tune the device to have the light beam split it exactly in half between two photodiodes, the summary output from these photodiodes will be zero. They actually both produce the same voltage, and we actually compare the voltage which is produced, or current which is produced by two photodiodes. If the currents are equal, so the photo amplifier will provide a zero. So when actually the current start to flow through the, or voltage, teeny voltage or current is applied to the photogalvanometric amplifier, the mirror is rotating a little bit, and this light spot actually is moved toward one of the second diode. That means that the current that flows through this one diode overwhelms the current, or actually will be higher than current that flows through the another diode. The difference in the current is measured by any method. It may be the really two voltage dividers when the both diodes are included, so some kind of, as an example, it's maybe such kind of circuit. Well, as an example, we may use such kind of circuit when we have a one diode and it should be in reciprocal reverse bias. One diode and some resistor, and the second diode and some resistor, and we actually measure voltage between these 2 points with instrumental amplifier, such kind. So when the diodes are equally illuminated, so here is some power supply, yes, and here is zero. Well, so when the diodes are absolutely equal illuminated, the current is same, and the voltage here is zero. If the light beam moves from one to another diode, one diode will pass more light, the second less light, and we got here the difference in voltage. This difference in voltage may be further proceeded, either it's already quite big enough, either it should be maybe amplified with the instrumental amplifier and becomes an indicator of how different the diode current is. The diode current in turn depends on the illumination, and illumination depends on the position of the spot, and the position of the spot depends on what is the current flow through this moving coil. It seems like it's a little bit redundant, so what is the reason? Why shouldn't we use an instrumental amplifier immediately? But actually, the voltages, what could be measured, on currents that could be measured using this type of amplifier is much more less than the instrumental amplifier could measure without high noise. So it's for very teeny measurement, especially if we are interested in really in some kind of very short pulses, and if it's short pulses come, we may use it oscillation of the signal afterward, and it's short pulse force to this blind spot to oscillate. We may use this oscillation to estimate the amplitude of the short pulse. So it's actually suitable for work with very short pulses too. Okay, and for today we probably finish today, and we discuss the next time we discuss in oscilloscopes and frequency and phase measurement. But it will be after the holidays, and I still try to write the description of how to calculate these two-order filters and put it in ortho. So, but I actually, when I do this, I send a message to everyone, so you will know that it's already put in on the orthos. What I will be actually, I still would be happy if you could learn by your own to find anywhere information about the oscilloscopes. If I remember, in orthos, so Where is my orthosis? Yeah. In orthos, you have such kind of the laboratory work, electrical signal measurement here, with a kind of guide to picoscope. So please find the description of the oscilloscopes, of the analog oscilloscopes in this lab number 1, and read, at least not, probably not thoroughly read, but just make yourself familiar with a picoscope, a digital oscilloscope. Yeah? At least look at the beginner guide, and generally you through the manual, or just at least review poster. So please, yeah, so you are assigned for the holidays to spend your time to read the operation of oscilloscopes in the lab number 1. I guess it should have this description here. I just check whether it is. Should be, if I remember. Yes, here is quite a thorough description of how the oscilloscope works. Just have to check whether it is. Oh no, sorry. There is no description for the oscilloscopes. I have to. Anyway, review, please review the operation of the digital picoscope, oscilloscope, what we use. So beginner guide and picoscope poster, and find anywhere. It's quite fine in Wikipedia. Look at Wikipedia on how the analog oscilloscope works. So, and I just add you. Yeah. Okay. Meanwhile, I will add the today lecture materials, and so please wait for my comment what I have to send you. So we actually finished today. If you have any questions, please. We're open to discussion now. I will add this lecture, which is not added yet because I have not translated all. I have only part to translate. I have to add it what we discussed today, and I will add it to Orthos too. I don't know, today or tomorrow, somewhere in the closest days. Not yet. At the moment, no. So you will be able to do this when I put the recommendation how to do this. So I'm going to make you an example, which we take another type of the film, how to work with it, and then you may take the second home task. But at the moment, no. At the moment, the argument what I just want you to do is to read about the analog oscilloscopes and review this description of the speaker what we use in our lab. Yeah. Okay. Yeah. Fine. So see you. Will be not the next week, but after a week. So bye bye.